In this problem, a car skids to a halt after traveling some distance L, and we're asked to find the initial velocity of the car before the brakes were put on and decide whether or not the driver was speeding. In order to solve this problem, we need to be able to identify the forces which do work on the car and use the work energy theorem, which states that the net work done is equal to the change in kinetic energy. We can write the change in kinetic energy as 1/2 times the mass of the car times the quantity of its final velocity squared minus its initial velocity squared. Because the car comes to rest, the final velocity is equal to 0, and we can write the work energy theorem as the net work is therefore equal to negative 1/2 times mass times the initial velocity squared. Three forces act on the car as it travels up the incline. These are the normal force, the force due to kinetic friction, and the gravity force. The first thing to note is that we can break up the gravity force into its x and y components using a tilted coordinate system like the one I've drawn here. In this coordinate system, the x component of gravity is therefore equal to mg times sine of this angle theta, which is also equal to the incline of the ground. The y component, similarly, is equal to mg times cosine of this angle theta. In terms of the work done by these three forces, we can immediately say that the work done by the normal force is equal to 0 because the normal force is acting in the direction that's perpendicular to the direction in which the car is moving. So, work done by F normal is equal to 0. The work done by the gravity force is equal to negative times the x component of the gravity force times L, which is the distance over which the car comes to a halt. The work is negative because the x component of the gravity force acts in a direction which is opposite to the direction in which the car is moving. Substituting in this expression, we see that the work done is therefore equal to negative mg sine theta times L. Note that we don't consider the y component of the gravity force because this acts in a direction that's perpendicular to the direction of motion. The work done by kinetic friction is equal to negative times the friction force times the distance L. Again, this work is negative because friction is acting in the direction opposite to the direction the car is moving. Friction is equal to the coefficient of kinetic friction times the normal force. Using Newton's second law, we see that the normal force must be equal to the y component of gravity because the car is not moving in the y direction. Substituting in this expression, we see that the work done by kinetic friction is equal to negative mu k times mg cosine theta times L. At this point, we can use the work energy theorem to solve for an expression for the initial velocity of the car. The net work is the sum of the work done by gravity plus the work done by kinetic friction plus the work done by the normal force. Substituting in the expressions that we just derived for these three works, we simplify and solve for the initial velocity to find that the initial velocity squared is equal to this expression here. All that's left now is to substitute in the numbers given in the problem statement, and we find when we do so that the initial velocity is equal to 19.89 meters per second. The speed limit for this road is 22.35 meters per second. Because the initial velocity is less than the speed limit, the car was not speeding when it slammed on the brakes.